Matrix operator nodes. We only have a small assortment of these guys, and there's not a lot, at least for the moment, that we can do with matrices. But they do come in useful here and there, mostly to do with rotations. The first two, the HPB matrix and matrix HPB, basically these take our right, up and forward, which are of course direction vectors, represented in the viewport here by our X, Y and Z handles. Of course, when an object rotates somewhere, then its local axes are, of course, realigned, and so these three vectors represent the item's rotation. So the rotation can either be described as heading pitch bank, as we're used to in Euler system, or in a vector system, by describing the direction of the three spatial axes. So all these do is convert us back and forth. The HPB matrix takes an Euler rotation and outputs a rotation matrix. The matrix HPB takes a rotation matrix and outputs an Euler rotation. Simple as that. And we see these used a fair few times throughout these tutorials when we've been setting rotations on things or matching rotations or looking up positions of things and rotating toward them and so on. Transpose matrix. Basically, transpose matrix just inverts a matrix. We saw the basic format of matrix notation back in the vectors video in the fundamentals section. It's worth returning to that notation here to explain transpose, because it's one of those situations where what we see done with the notation is a very close match for what we actually see happening in terms of space. What the transpose does is it swaps the rows with the columns. The effect this has is to mirror the values across this line, so these three diagonals stay the same. So we still get the A, E and I, but otherwise C moves down here, B over here, D over here, G over here, H over here, and F down here, mirrored in that diagonal fashion. So you see, if we take the rotation of something, for instance here the null 2, and we take its rotation matrix of right, up and forward into a transpose node, convert that back into a rotation of course, and feed that as a rotation for something, in this case our third null there, we can see that whatever we turn one on, the other turns the opposite amount. We don't have to do this coming from item info when we do want to do a reverse constraint like this. The world right, up and forward are the transpose of the right, up and forward here. You would generally use this when you needed to grab the same inverse rotation information, but coming from somewhere else, some constructed rotation, where you didn't get a source world right, up and forward like you do on this node. The multiply matrix is, well, not a particularly complex node, but matrix multiplication does have some pretty complex uses, many of which have to do with adding up sets of data over time or other things. Not something that your average user is going to turn to a lot. The kinds of techniques that you would commonly use matrix multiplication for. Basically, what it does is it multiplies one matrix by another. This isn't done in the straight add-subtract fashion that we describe with the basic math nodes, for instance. And I'm not going to talk about how it's done, because there's little point. But to give you a visual example, we will just hook a couple of things up here. So I'll take the right, up and forward as my first matrix, my A matrix. That's the rotations matrix for this null here, and I'll multiply it by the rotations matrix for the other null. So take its right, up and forward, those over to the matrix HPB to convert them back into a regular Euler rotation. And what we see that we get is that this one follows the first, but it also follows the second, and of course we're getting the combination of both. So it's much like the rotations are being added on top of one another. That's the effect of matrix multiplication, in the sense of rotation matrices, which is what we commonly have access to here in Lightwave. There is, however, something interesting to note with this, and that specifically is the fact that we are still multiplying individual three-dimensional vectors. What's not being taken account of in the multiplication of these rotations is any kind of Euler rotation order. The fact that we're converting here doesn't make a difference with that. So, let us note that what we get in terms of constraining when using the multiply matrix is a kind of angular constraint. If I turn null 1 here on heading by about 90, give or take, you see that I can turn this on heading, and it of course gets added on, so that's predictable, but notice what happens if I turn it on bank here, is our other is pitching. It's going in the same world direction that our second null here is turning. And equally, if we roll this on pitch, then that goes around on its bank axis there. The addition is based on the angles and directions of these vectors, rather than just a HPB addition. But the order matters as well. Let's say we take it the other way, and I put this at 90 on heading. We see that rotating this one now on pitch still rotates our destination item on pitch. However, when we go to its bank, we get heading rotation, and when we go on heading, we still, of course, again get the heading rotation. And the reason for it is twofold. As I've said, the rotation order of the Euler system itself, but also one of the facts of matrix multiplication, and that is it works different to standard scalar multiplication. With scalar multiplication, A times B is the same as B times A. With normal vector multiplication, vector A times vector B is the same as vector B times vector A. With multiplication of matrices, it is not so. A times B is not the same as B times A. So if I swap these guys over here, what we will see I get is a different behaviour again. Essentially, I have swapped the behaviour. So this null 1, which is here, that I have now slotted into the A, is essentially being looked at second, as it were, in terms of this angular constraint. So there we go. There's not an awful lot else to say about the matrix multiplication, at least not without getting pretty technical, and there's little use for that here. Certainly, if you do wind up going further, then there's plenty of uses to be found for it. Lastly then, we have the transform to node, which takes a vector and uses a matrix to transform it. In this case, even though it says right, up and forward, this doesn't mean right, up and forward in the same kind of sense as the rotations that we've seen so far. This is just the top row, middle and bottom row of the matrix. What it provides is a linear transform, so the vector that comes in gets moved by its existing value multiplied by the matrix. What this is usually used for is to perform linear transforms on geometry, such as our little bunny here. A linear transform basically just means a movement in a straight line. So a vector, taken as a location in this sense, a point in space, is moved in a straight line in space in the direction described by the matrix, or the amount described by the matrix. So let's for instance take the spot info of our bunny here, and we'll take the object spot as our vector, coming in of course here as a vector set essentially, so all of the different spots locations. What we have here is a standard identity matrix, so xx1, yy1 and zz1, everything else 0. If we pop this into displacement, we'll see our bunny grows. Normally, multiplications by an identity matrix have no effect on the matrix that they're multiplying, but in this case we're transforming a vector. And so what is happening, if I unhook this for a moment, we see that for instance the points here at the edge of Bunny's cheek are, well, our grid is 1 meter, we see that they're 5 meters out here. So by sending them their existing amount times 1, they come out to 10 meters. They're currently at 5, so they get transformed by 5 times 1. And that happens for every point, so essentially our thing just doubles in size. If we're keeping them at the same size, then we keep a total 0 matrix. What we'll see then is what happens when we start pushing things off in the other directions. If we punch 1 into y, in the top row's value here, we see that he shears, and he shears across in the x, because of course this direction vector as a whole is describing the x displacement. Because we have 1 in y, then he's shearing high up in y, but not down here where y is 0. Similarly, we can do the same thing on z, and in this case he appears to shear in this manner. And we notice that his back end here is going forwards in z, whilst his front end here is coming negative in z in the shearing. This of course is because we're plotting the x position of each vertex. And so of course these ones are on the positive x and those are on the negative x. A good way to get a more visual idea of this is to use the world spot here, and of course make sure that I've gone to the before world displacement mode. Then if I punch 1 into the x for the y component, the y row, then we see that as I translate it on x, the points translate in y. If I were to do that here, then pushing him in X pushes him across in Z. Had I done it here, put the Y into the bottom row for Z, then moving him on Y would smush him around on Z. Basically, it allows you to transform the space within the reference space and do other such things. As well, of course, as produce the opposite, or inverse, as we can see there. So really, this is starting to be the sort of node that you use when you're constructing certain kinds of deformation or displacement, and as such is a much more techy node. It can, however, have its uses, just grabbed quickly by the artist, on those occasions when you need a quick shear effect, or when you need one animated. See, I've grabbed the null there, and I'm just going to use its rotations matrix to drive the vector transform, and we'll see that when I rotate this null around, we can see this rather unusual effect I get. I have, of course, just got the null being rotated somewhat haphazardly there, as you can see, but you can see that the linkage between its rotation and the scaling and shearing of our object from the matrix transform. So a little bit of care to animate perhaps if you do find yourself doing this sort of thing for something, and not that commonly useful admittedly, but of course good to know what it does, and also helps us to understand a bit more about the way that our vectors and matrices work in Lightwave and the kind of tools that are available to us. And so with that, those are the matrix operator nodes.